All right, welcome to The Explainer. Today we are looking at a brand new AI model that might just force us to rethink how we build machine intelligence. And this is an approach that isn't about just making things bigger, but about making them smarter, by taking a page directly from the human brain's playbook.
So let's just dive right into a paradox that's been bugging AI researchers for a while now. You have these massive AI systems, right? Large language models, LLMs. They can write stunning poetry. They can write complex code, and yet they completely fall apart on basic reasoning tasks that, frankly, a child could solve. Things like a simple game of Sudoku. How is that possible?
And this isn't just some weird little quirk. No, it points to a really fundamental problem with how we're building AI right now. The researchers behind this new model, they put it perfectly. They say that even these giant AIs are built on a paradoxically shallow foundation. That core structure, called the transformer, has a fixed depth. It literally puts a cap on their ability to do deep, multi-step thinking.
You know that popular trick, chain of thought, where you ask the model to kind of talk itself through a problem? Well, it turns out that's just a workaround. The researchers here call it a crutch, and that's because it's super unreliable, it can get totally thrown off by one little mistake, and it needs a ridiculous amount of training data to even work in the first place.
The thing is, just adding more layers to a standard AI, making it deeper, it doesn't fix this reasoning problem. I mean, look at this chart from the research. They tested it on hard Sudoku puzzles, and performance just hits a brick wall. It flatlines. The old way of doing things has pretty much maxed out.
So, okay, if making models bigger or deeper isn't the answer, where do you even look for a solution? Well, it turns out the answer might be sitting right inside our own heads.
Our brain is, the ultimate reasoning machine. And one of its secret weapons is something called hierarchical processing. It's this clever strategy where different parts of the brain team up, but they work at different speeds and on different levels of the problem.
Think about it like a company, right? You've got the high-level manager who does the slow, big-picture thinking. They set the overall strategy. And then you have the team of workers who are super fast and efficient, and they just execute the nitty-gritty details, step by step. It's an incredibly powerful way to get things done.
So, taking a cue directly from this biological blueprint, the researchers created a totally new kind of architecture, the Hierarchical Reasoning Model, or HRM for short.
The HRM basically copies that brain structure with two key parts working together in a loop. You've got the high-level manager for the slow, abstract planning, and then you have the low-level worker for the fast, detailed work. The manager sets a goal, the worker crunches the numbers for that one step, reports back, and then the manager adjusts the plan and gives the next task. It's this constant back and forth between strategy and execution.
And what you get from this design is pretty amazing. The HRM can think way more deeply about a problem, but it stays stable and easy to train. And get this, it doesn't need to be pre-trained on the entire internet, and it doesn't need any of those fragile chain of thought prompts.
Okay, so the theory is beautiful, it's elegant, but here's the real question. Does the thing actually work? So let's see how it did when they pitted it against some of the biggest AIs out there. First, you gotta understand the challenger here. The HRM model that used has only 27 million parameters. Now, to put that in perspective, that is tiny. We're talking about a rowboat going up against billion-parameter battleships. And then there's this. For every single task, it was trained from scratch with just 1,000 examples. That's it. No pre-training on huge datasets, just a handful of practice runs to learn from. All right, now for the main event. On these Sudoku Extreme puzzles, which are designed to be insanely difficult. Look at this. Every single one of the massive, state-of-the-art models scored a 0. A big fat nothing. Not one puzzle solved. Meanwhile, the tiny little HRM, it solved over half of them. And it wasn't a fluke. It's the exact same story when they asked it to find the shortest path in a complex maze. The competition? Completely lost. Zeros all around. HRM found the right path nearly 75% of the time.
The same pattern holds up even on the ArcAG challenge, which is a major benchmark people use to measure progress towards real artificial general intelligence. And again, our little 27 million parameter ArcHM smoked its much, much larger competitors.
including some very well-known models.
So look, these results they're more than just impressive numbers on a slide. They point to something really profound, something deep happening inside the model while it's learning.
But here's the real kicker. This is the part that is just mind-blowing. The most groundbreaking discovery came when the researchers actually peeked under the hood to see how it was doing this. It hadn't just learned to solve puzzles, it had spontaneously learned to organize its own internal wiring in a way that looks just like a brain. This comparison is just incredible. On the left, you're seeing a map of neural activity in a mouse's brain, where the higher-level parts show more complex activity. And on the right, that's the HRM. It developed the exact same hierarchical pattern all on its own, just through the process of training.
The numbers just seal the deal. This ratio of complexity between the manager and worker in the trained HRM, it's shockingly similar to what you see in a mouse cortex. But look at an untrained model. It's totally flat. There's no hierarchy at all. So this brain-like structure wasn't programmed in. It emerged as the best way to solve the problem.
And that brings us to the most important point. By simply training this model to reason, it autonomously discovered one of nature's own fundamental tricks for building a flexible and intelligent system.
So what does this all mean? Well, it completely challenges the bigger is always better idea that has dominated AI for years. It opens up this fascinating new path, a much more efficient one, toward creating machines that don't just mimic intelligence, but can actually reason. So the question it leaves us with is, have we just stumbled upon a key to unlocking true machine intelligence?